The topic of the video is solving the problem of linear harmonic oscillator using operators method. In this video, we will actually find out the energy eigenvalues and eigenfunctions of linear harmonic oscillator using raising and lowering operators. We can define linear harmonic oscillator as a particle of mass m and it's attached to a spring of force constant k and executing the oscillatory motion in one dimension as shown here on the right hand side. And for the system we can write the Schrodinger equation like this with the state function dependent upon both x and t, and the Hamiltonian operator given by p square by 2m, which is the kinetic energy, and of kx square, and that's the potential energy, where this k by m is also called as omega square, which is the angular frequency squared of the oscillator. So we can write down the h operator like this and call this as equation number 1. Since h is independent of time, we can actually select our state function psi as some exponential like this, and then a function phi which depends upon only x variable. And if you plug in this in the Schrodinger equation, we actually get h phi is equals to e phi. So to find out what these phi's are and what is the expression for e, we actually use raising and lowering operators. So we define a plus operator in terms of the position operator x and momentum operator p like this, and a minus operator is actually dagger of this operator. So instead of in the place of I will be getting minus I, so it is defined like this. If you do the product a plus into a minus, we can actually write them down like this, and if you simplify we'll get here a term in bracket as xp minus px. So it is actually the commutator of x with p, so that we know as ih cut. So we can actually go on simplifying this. So what we see is that on the right hand side we'll be getting terms similar to the Hamiltonian operator that we had in equation number 1. So we can actually write down that Hamiltonian operator in terms of these a plus and a minus operators like this, and we'll call this as equation number 2. And if you find the commutator of a minus with a plus, which we define like this, and if you substitute for those a minus and a plus values, and if you use again the fact that commutator of x with p is ih cut, we actually quickly find that a plus and a minus commutator is giving you answer 1, which we can call as equation number 3. We can also find the commutators of x with a plus, so we can actually substitute the value of h here, and we can make use of the fact that commutator of a plus b with c is equals to a with c plus b with c, and in case if it's a product, that is ab with c, then we can write a outside and we can write b with c, and then a with c and b outside. So we can write down this commutator as a summation of two terms like this, and we can again write this and into two commutators like this, and it's a constant here, so this commutator will give you answer 0, and here we have similar kind of terms here. So commutator of an operator with itself is 0, so we'll get the commutator of h with a plus as this as we call equation number 4. Similarly, we can find the commutator of H with A minus, and uh, if we actually progress with the steps which we had in the earlier calculations, we'll be getting similar kind of answer, that is equation number 5. If phi is a eigenfunction of operator H with eigenvalue E, then the eigenvalue equation can be written as H phi is equals to E phi. And if you take this eigenfunction, which is a plus into phi, and if you want to find out its eigen value, then we can operate H on that. And if you follow a few steps, like if you add if you subtract a plus h, and then if you add a plus h, the answer won't change. So but if you actually take these two terms together, we can actually write that as a commutator of h with a plus, and we can have this as it is. But from equation number 4, this h with a plus was a plus into h cut omega. So we can substitute this, and if you operate phi here, and then we can operate phi in the second term also like this. So here when h operates on phi, it will give you e. So if you want to write down a plus into phi outside, we can write this in bracket. So we'll get e plus h cut omega in the bracket. So we can say that a plus into phi is eigenfunction of h with eigenvalue e plus h cut omega. Since this a plus has kind of raised the energy from being e to e plus h cut omega, we say a plus as a raising operator. Similarly, if you want to find out the eigenfunction, eigenvalue of the eigenfunction a minus into phi, which we can write h into this one, and then h a minus can be kept as it is. But if you subtract a minus into h, and if you add a minus into h, the answer won't change. But those first two terms can be written as the commutator of h with a minus, and then but from equation number 5, that commutator is minus h cut omega into a minus. And if you operate phi on them, we'll quickly see that it will give you eigenvalue e minus h cut omega into eigenfunction e minus phi. So we can say that a minus phi is eigenfunction of h operator with eigenvalue e minus h cut omega. And since this a minus has lowered the eigenvalue by h cut omega, we call this a minus operator as lowering operator. If the smallest eigenvalue of h is e naught, and if the corresponding eigenfunction is phi naught, then we can write the eigenvalue equation as h phi naught is equals to e naught into phi naught, and this e naught is actually called as 0 point energy. Since phi naught is the eigenfunction of lowest possible eigen value, then if you operate a minus on that, it cannot lower it any further. So so the answer will be 0 for that. That means if you take a minus into phi naught, it should be equal to 0. And if you multiply that with a plus operator on both sides, we'll be getting this as equation number 6. The equation number 2, which we had for h operator, can be inverted for a plus into a minus. So we'll get this expression here, and if you substitute that in the earlier equation, then we can get this operating on phi naught. But h phi naught is actually e naught into phi naught. That was from equation number 5. So we can get e naught expression as half h cut omega, because phi naught cannot be equal to 0, and we call this as equation number 7. Wait a second, here it's not from equation number 5, but h phi naught is equals to e naught into phi naught. That's why we'll get this expression here, and E0 is equals to this, as we call equation number 7. Since A plus is a rising operator, A plus operating on phi naught will be eigenfunction of H with eigenvalue H cut omega plus half H cut omega, which is 1 plus half into H cut omega. And we can say that A plus into phi naught will be eigenfunction of H with the corresponding eigenvalue of 2 plus half into H cut omega. And A plus raised to n into phi naught will be eigenfunction of H with eigenvalue n plus half into H cut omega. And if you call phi n as A plus raised to n into phi naught, and if you consider this expression that H acting on phi n should give you En into phi n, then we can say that En is n plus half into H cut omega, which we call as equation number 8. And this equation is telling you that the energy of linear harmonic oscillator is actually kind of quantized, because here n can take only values like 0, 1, 2, 3, etc. We can say that for n plus 1 level, the eigenfunction can be written as phi sub n plus 1, and it is equals to some kind of a constant c sub n plus 1 into A plus acting on phi n. And if phi n plus 1 and phi n are actually normalized in Dirac notation, we can take their scalar products as ones. So if we take the scalar product of phi n plus 1 with phi n plus 1, on the right hand side we can substitute for them. And since the thing which is in bra vector, if it goes the front side, it will become dagger of itself, and if it's coming from kid, then it won't have any dagger. We can write like this. So this, on the left hand we can write 1 for the scalar product, and here we can write Cn plus 1 modulus square, and this like this. But the equation number 2 was telling you what H is like in terms of A plus and A minus, and then 3 was telling you the commutator of A minus with A plus is equal to 1. So from that we can write A plus into A minus as A minus plus A minus into A plus minus 1. So we can express A minus into A plus as H by H cut omega plus half. So if we substitute the value that we got for A minus into A plus into the above equation here, we can actually see that H acting on phi n will give you n plus half into H cut omega. So H cut omega will get cancelled here and here, and we get n plus half will become and then the phi n with phi n bracket will be 1. So we'll get c sub n plus 1 is equals to square root of 1 over n plus 1. So we can write that phi sub n plus 1 is equals to 1 over square root n plus 1 into A plus acting on phi n. And if you take n is equals to 0, then phi 1 is equals to this, and phi 2 is equals to A plus acting on phi n, but divided by square root 2. But in place of phi 1, if we substitute the expression that we had here, we can get phi 2 is equals to A plus square divided by square root of 2 into phi 1 phi naught. Similarly, we can write down that phi 3 is equals to A plus divided by square root 3 into phi 2. And in place of phi 2, if we substitute the thing that we had earlier, then we can write down that phi 3 is equals to A plus cube divided by square root 3 factorial into phi naught. Similarly, we can write down that phi n is equals to A plus raised to n divided by square root of n factorial into phi naught, and call this as equation number 9. This is the expression for eigenfunction of linear harmonic oscillator in operators method. And the equation number 8 was giving you the eigenenergy of linear harmonic oscillator. That's it in this video, and thanks for watching.